Hello everyone, so in this video I'm going to solve two BJT examples, and I'm going to teach you how to choose between the pi model and the T model, which one of them is the one that you should be using as a small signal model when you want to solve for a BJT example. Okay. So let's get started with this first example that says that you have a BJT transistor, and the transistor is biased as a common emitter. Okay, the input is from the base, and the output is from the collector. Okay, and what is required is to find V output over V input, the value of the output relative to the input, the gain of this transistor. So what we do is that we solve the problem first in the DC mode, then find some values to use it in the AC mode. Okay. In the DC mode, we switch all the capacitors to an open circuit. Okay, and all the sources, the AC sources, to a short circuit. Okay. So this becomes the value of the circuit, the equivalence, the DC equivalent circuit. Right? What do we want to do? We want to find what is called GM, the transconductance of the transistor. Right? And its value is equal to VT is equal to IC over VT. VT is equal to 25 millivolts. Right? So the question is, what is the value of IC? If I could find the value of IB, I could multiply it by beta and then get the value of IC. So what I'm going to do is that I'm going to find the value of this current, which is IB, right? And this IB is the one that is going to be multiplied by beta to find the value of IC, right? How do you find IB? Let's take KVL in this loop. You expect to see positive 0.7 volts here, and the current is passing from the high voltage to the low voltage. So that's positive and that's negative. So KVL in this loop is 3 minus RB IB, okay, minus 0.7 volts equals 0, right? What is the value of RB? RB is given to be equal to RB is given to be 100 kilo ohms. All right. So the value of IB is equal to 3 minus 0.7 over 100 kilo ohms, which is equal to 2.23 microamperes. Okay, do the math, you get this value. Okay, so in that case, what is the value of IC? IC is known to be equal to beta multiplied by IB, and thus it is beta is 100, so 2.3 milliampere. Do the multiplication, you get 2.3 milliamperes, which means that the GM is equal to 2.3 over 25, which is roughly speaking equal to, this is by milliampere, this is millivolt, so this is roughly speaking this is 92 milliampere. 92 milliampere per volt. Right? 92 milliampere per volt. Okay? And then we calculate the value of R pi. I'm going to tell you what we are going to use in terms of these two values. But these are the DC, the values that are going to be used in the AC equivalent circuit. Okay? what is the value of R pi? R pi is equal to beta over Gm, which is equal to 100 over 92 milliampere per volt. So R pi is equal to 1.09 kilo ohms. Okay, so right now we have the value of Gm and we have the value of R pi. Okay, so now are we done? Yes, we're done. Okay. What do we do in order to get the value of the V output over V input? These are V output over V input is an AC quantity, and thus you need to calculate the AC equivalent. You need to use the AC equivalent circuit in order to find this quantity. All right. So we have two equivalent circuits. We could use either the pi model or the T model. Okay, that's the pi and that's the T. It's called hybrid pi model or hybrid or the T model. Okay. It turns out that in this particular example, it is much easier to use the hybrid pi model. I'm going to solve first using the hybrid pi model, okay, and let you know later on why the T model is difficult to be used, although it gets you'll be able to get the same answer. Okay, what is the pi model? The pi tells us that you draw the circuit in this form, where you have a dependent current source. Its value is equal to Gm V BE, where this is the B and this is the E. So this is V BE, right? And the value of this resistor is equal to R pi, which is what you have calculated in the DC equivalent circuit. Okay? And then, so that's the value of the B. So you put three nodes, collector, base, and emitter, do the current source, and then draw the resistor, right? So after that, you need to connect. Okay, so if you were to use the value of the T model, in that case you would be writing here RE, and this is Gm VBE. VBE. But remember that this is RE, it is not R pi. What is the value of RE? RE is equal to alpha over Gm. So R pi is equal to beta over Gm, and this is equal to alpha over Gm, which is the same as you calculate Vt over IE. Alright, so if you want to calculate the RE not using the Gm but using the Vt, you can calculate it using the Vt, using the emitter current. Okay, so let's get going through this model. Where did we have the source? We had the source here, alright, originally. That was the source, the AC source, the input, and that is the output. We had a capacitor, and it becomes a short circuit in the AC equivalent circuit. Alright, the emitter is connected to the ground, so that's the ground. Then this voltage source is a short circuit because it is DC, right? And then we have this AC, V input, and this is called RB. Alright? At the output we have, from the collector we have a resistor passing to the ground. The VCC becomes a ground. Okay, this is RC, and this becomes the ground because it is a short circuit in the AC equivalent circuit. And the V output is coming at the collector. So this is the V output. Alright? So this becomes the equivalent circuit of the transistor, the bipolar junction transistor. And right now what we want to do is calculate the value of V output in terms of V input. And thus we will be able to divide the whole equation by V input and get the value of the gain. Alright? What is the value of the V output? There is a current passing here which has a value of Gm VBE. So the current that passes here makes a potential difference, and the value of the potential difference equals negative the current Gm VBE multiplied by the value of the resistor. Why negative? Because ideally this is the output. Okay, so the current should pass from above to below, from the top to the bottom, right? And that's why we have, but this, which is opposite to this current, so that's why we have this negative value. What is the value of VBE? VBE is a voltage divider rule. Why? Because the current passing through this R pi is equal to the current passing through RB, which is I base. Okay, this current is equal, so you end up with a voltage divider rule, and thus VBE is equal to V input, right, multiplied by R pi over RB plus R pi. Okay, so that's a voltage divider rule. R pi over RB, but that is because the current here is passing the current passing through R pi is the same as the current passing through RB. That's why we were able to get this voltage divider rule. Divide the entire equation by V input, you get negative Gm R pi over RB plus R pi multiplied by RC. Okay? Alright, so what is the value of Gm? 92 milliampere per volt. 92 milliampere per volt. And R pi 1.09 kilo ohms. 1.09 kilo ohms over 100 plus 1.09 kilo ohms. This is by kilo, this is by kilo, this is by milli, and this is 3 kilo ohms. Okay? Thus, you end up, roughly speaking, approximately equals negative 3 volts per volt. And that is the value of V output over V input. Okay? So, this is the method that I follow in order for me, this is the method that I follow in order to get the V output over V input. I use the AC equivalent circuit after calculating the parameters of this AC equivalent circuit. Okay? So the question right now is, why didn't I use the T model? Because the T model is going to be difficult. Alright? Why is it difficult? Because if you want to really calculate the value of V output over V input, where is V output? V output is at the collector. Okay? That is the V output. Right? And you have a resistor here, which is called RC. Okay? And you have the value of RB here, and that is the input. Okay? So this is RB, right? If you want to calculate the value of V output, you multiply the resistance RC multiplied by this current gives you the value of V output. Gm, the negative sign, VBE, RC. But the problem is that this VBE cannot be obtained using a voltage divider rule. Why? Because the current passing here is not the same as the current passing here. You need to do some sort of Kirchhoff current law. It is doable, but it is much difficult than this systematic procedure, which can be done without doing any KCL. Alright? So when do I really use the pi model? When I use the pi model whenever I have a common emitter. Right? This emitter is common between the input and the output. Okay, common emitter. Alright? Why? Because the common emitter, I need to differentiate, I need to have a separate circuit for the input and a separate circuit for the output. It facilitates the analysis a lot. Alright? On the other hand, this does not work when we have a common emitter. It does not work that easy. Alright? But it does work when we have a common base. Let's assume that you have this is common, alright? This is the base is common, but the input is fed through the emitter, and the input is fed through the emitter. And if you have a battery here, it doesn't hurt as well. Okay? Okay? In that case, this equivalent circuit becomes better. Why? Because I would be short-circuiting, alright? I would be, and that's the output. So that's V input, and that is V output. Okay? I would be short-circuiting the base, right? And the input is fed from here. Okay? So in that case, you will be able to obtain the value of VBE through this loop, alright? As a direct function of V input. In that case, VBE is equal to the negative of V input, negative V input, right? And thus, you can obtain the value of VBE as a function of V input directly without the need to use any KCL, right? So whenever you have a common base, in that case, you need to use the T model, which makes the analysis much easier, right? And whenever you have a common emitter, use the pi model. Because the pi model has a common emitter. By nature, it differentiates. It kind of differentiates or the output circuit, output loop from the input loop. Okay, it has this nice property, right? So let's move on to the another example where we have this kind of connection, which is a common base connection. Okay. Okay, so now in this example we have a BJT transistor as well, but this BJT is a PNP BJT, right? The arrow is coming to the transistor, so it is a PNP BJT, right? So the question is, how can you get V output over V input given that beta of this transistor is 100, which means that alpha is 0.99, right? So, as usual, we'll be solving the DC and then solving the AC, right? But for this transistor, the V input is fed through the emitter. Remember that the emitter is the terminal that has the arrow, while the collector is the terminal that does not have the arrow, and the base is the third terminal, right? The V input comes to the collector, and V output comes out of the V input comes to the emitter, and V output comes out of the collector. Okay, so if you want to, and that's why it's called a common base, because the base is neither an input nor an output. Okay, so let's have a look at the DC equivalent circuit. The DC equivalent circuit means you disconnect the capacitor, okay, and disconnect the input source. And if you want to calculate the value of IE or IC or IB, we basically want GM, right? GM is equal to IC over VT. So let's find the value of IC. How do we get the value of IC? Well, if you look, 25 millivolts, that is for the VT. If you want to get the value of IC, which is this current, you do not have anything, you do not have the value of VCB. You do not have this value. And thus, you cannot make use of this loop, right? So what we can make use of is this loop. Why? Because we know that the value of this is 0.7 volts. From the emitter to the base is 0.7 volts. The emitter in the PNP is higher than the base by 0.7 volts, roughly speaking. Okay? And thus you can take KVL in this loop, right? Which gives you IE is equal to 0.93. The 10 volts minus the voltage drop on this transistor, on this resistor, minus the 0.7 gives the 0.9, gives 0, which means that IE is equal to 0.93, given that RE is 10 kilo ohms. Alright? So the IC becomes alpha multiplied by IE, okay, which means that IC could be obtained, and thus this becomes the GM, the value of GM becomes 36.8 milliampere per volt. Okay, 36.8 milliampere per volt. Okay, so that's the value of GM. What do we need to calculate as well? Since we are going to use the pi, the T model, then we have to calculate the value of RE. What is RE? RE is equal to alpha over 36 over the GM, which is equal to 0.99 over 36.8, which is, roughly speaking, equal 27.2 ohms. 27.2 ohms. So that is the R pi, RE. Okay? So let's draw the equivalent circuit. Of course, you could use this equivalent circuit directly. The AC equivalent circuit right now is what we are heading for. You could use this AC equivalent circuit directly. And it is the T model. We know that we're going to use the T model's AC equivalent circuit. Yes, you could use it, but however, I like to write it in this format, which means that the emitter is on top and the collector is at the bottom. So I write down that's the emitter, that is the collector, okay, E, C, okay, and then flip this. So the collector, from the collector to the emitter, I find a dependent current source followed by RE. So a dependent current source, okay, pointing up, pointing from the collector to the emitter, and then followed by RE, okay, and the value of this is GM VBE, okay, and then you have the base, but the base is on the right side, so this is the base, and it is shorted to the ground, okay. The emitter has a resistor passing to the ground, so a resistor passing to the ground, and then the input, which is connected here because there was a capacitor. There was a capacitor here, and the capacitor is a short circuit. So you end up with the input from the emitter to the ground. Okay, and the value of this is 10 kilo ohms. Okay. What about the collector? The collector has a resistor and then to the ground. Collector has a resistor and then to the ground. Okay? Let's see the T model, how we are going to solve this. What do we want? We want the V output, which is this value, okay, which is the value of on the 5 kilo ohms. These are 5 kilo ohms from the collector. Okay? V output is equal to that is the current passing here multiplied by the 5 kilo ohms. What is the value of the current that passes here from top to bottom? Its value is equal to negative GM VBE. That is the value of the current multiplied by 5 kilo ohms. Okay? And then what is the value of VBE? VBE is equal to BE. Okay, this is the value of VBE, which is the value of the base minus the emitter. Okay, negative GM VB is 0. V emitter is V input. So this is VB minus VE, okay, multiplied by the 5 kilo ohms, okay, which means that you have GM V input multiplied by 5 kilo ohms. Alright, we're missing anything? No, we're not. So V output over V input equals GM multiplied by 5 kilo ohms, which is, what is GM? 36. So multiply 36 by, you end up with roughly speaking, 184 volts per volts. Okay? So this is the V output over V input. Okay? So as you can see, the T model is extremely easy when you have a common base. Why? Because the common base, because the T model isolates the input from the output. Okay? On the other hand, if you want to use the pi model, Okay, so that is the current source, and that is the emitter, and this is R pi. So the base is connected to the ground. Okay, the base is connected to the ground. The emitter has a resistor, and then the emitter has a resistor, and then to the ground. Okay, and the emitter has an input source. So that is the input source. While the collector has a resistor and then to the ground. A resistor and then to the ground. Okay? So as you can see, if you want to calculate the value, what is this value? This is GM VBE, which is this value, VBE. So that is the base, and that is the emitter, and this is the collector, where this is V output. Okay? So if you want to calculate the value of V output in terms of V input, you need to calculate this product, which means that you have to find the value of VBE. VBE is not a direct function in the input. It's the voltage on this resistor. In order to calculate the voltage on this resistor, you have to calculate the current coming here. Which means that you have to first calculate the current coming here, and then do a current divider rule, and then be able to calculate the value of the current, which maps you can calculate the value of the current in terms of the V input, and thus you'll be able to calculate the value of VBE in terms of V input and then substitute. But that's a very long way. Okay, so that's why the T model is always easy whenever you have a common base. Okay? Whenever you have a common base. Right? So, the last thing that I want to tell you is the following triangle that I always find. Actually, I'm going to put it in the form of this. So, usually what we have is we have something like that. That is the collector, that is the emitter, and that is the base. Okay? So I'm going to draw this triangle. Okay? That's the collector, and that is the emitter, and this is the base. Okay? So, always the base is an input. Always the base is an input. Right? The base is always an input. And that's why I wrote down input here and input here. The collector is always an output. Right? The collector is always an output. Okay? So, which means that this could be either input or output. Okay? So, what does that mean? Let me step back. The base is always an input, which means that if you have a base, if you have a common emitter, and you have a collector and a base, one of them is the input and one of them is the output, then the base is always an input and the collector is always an output. Okay? So if you have, forget about this, if you have a common collector, a common emitter, then the base is always an input and the collector is always an output. If you have a common collector, then the base is always an input and the emitter is always an output. That is a fact. Okay? You never find a common collector having the base as an output and the emitter as an input. The base is always an input. Okay? What about if you have a common base? The common base, it's always the case that the output is at the collector and the input is at the emitter. Okay? That's usually, so whenever I tell you I have a common base, as this example, I have a common base, this means that the collector and the emitter, one of them is the output and one of them is the input. And this triangle tells us which is which. Output is at the collector and the input is at the emitter. Output here at the collector and the input is at the emitter. Okay? So this triangle, I find it very easy to comprehend and to memorize the most commonly used configurations of BJT transistor. Okay? Hope this helps you guys, and please let me know if you have any questions.